Okay, let's do a sensitivity practice problem. So we've got a linear program. Here's the original problem. And then after using the simplex method, here's the optimal tableau that we end up at. Okay, so let's start off with the question of what's the current basis? Well, how do we find that current basis? We look for the standard basis vectors. In this case, we've got our first standard basis vector is always z, right? Usually I don't count that as being part of the basis, but then the next standard basis vector is x2 and then x1. Okay, and maybe then as a side note, our non-basic variables are going to be x3, s1, and s2, where s1 and s2 are the introduced slack variables for our two constraints. Okay, so that's kind of the warm-up question, but it will be helpful to help us answer the rest of the questions. But next question, find the range of values that the right-hand side of the second constraint. Okay, so here's the second constraint here. Here's the right-hand side. It's currently equal to 6. Find the range of values that right-hand side second constraint can take on while maintaining the optimality of the current basis. Okay, so go ahead and give that a try, and we'll come back in a second. So, give it a try. Hopefully you found the right answer, but let's go over the solution for B. So, how do we decide whether a alternate value of this will maintain the optimality of the current basis? Well, the consideration that we need to look at is we need that our modified basic solution has to stay greater than or equal to 0. Okay, if it goes less than or equal to 0, we've moved out of the feasible region. Okay, and what's this modified basic solution going to look like? Well, we'll still have the same B inverse matrix, but we'll be modifying our right-hand side B vector. Okay, and that's going to be our B matrix. We can read that off from our optimal tableau. That B matrix is exactly the columns corresponding to S1 and S2 for the two constraint rows. So this block here ends up being exactly B inverse. So don't have to worry about inverting a matrix. So that'll be -1, 1, 1, and -0.5. Okay. Our kind of alternative B vector we'll keep 4 for the first entry, and then the entry that was 6, let's just call that B2 bar. So an alternate possibility for what that second constraint right-hand side could be. So we want this to be greater than or equal to 0. Let's go ahead and compute out what this is. We'll do the matrix multiplication, and for the first entry, we'll get -4 plus B2 bar, and for the second entry, we'll get 4 minus 0.5 B2 bar. Okay, and we need that is greater than or equal to 0. That'll give us two inequalities. The first inequality will be -4 plus B2 has to be greater than or equal to 0, which if we add 4 to both sides tells us that B2 is greater than or equal to 4. The second one looks like 4 minus 0.5 B2 bar is greater than or equal to 0. If we add this term to the other side, that'll give us 4 is greater than or equal to half B2. And then we'll multiply both sides by 2, and that will give us 8 is greater than or equal to B2 bar. Okay. One of these is a lower bound, so the lower bound is 4, the upper bound is 8, and so our range of allowable values for that right-hand side that will maintain the current basis will be values between 4 and 8. Okay, and remember the current value is 6. it's in that range. That's a nice check to do that your current value should be within the range that will keep the current basis. Okay. So that is the values that B2, that second constraint right-hand side, can take and still have the same basis. Now, if B2 goes smaller than that, then we'll switch to a different basis. If B2 goes bigger than 8, we'll switch to a different basis. Okay, and so that's part B. Let's move on to part C. So part C asks, can we find the range that the objective coefficient of x2, which is currently C2 equals 4, that is this value right here. What's the range that it can take on while keeping the same current basis? Okay. So currently 4, what value is going to take on? Go ahead and give this a try. So hopefully you've given it a try and found the right answer, but let's talk it through. So one of the things to note before moving on is that x2 is exactly one of our basis variables, okay? And we see kind of our standard basis vector in there for x2, okay? So if this 4 changes, a couple things will change, okay? And that makes it a little bit more complicated than if a non-basic variable coefficient such as this 2 for x3 were to change, because x3 is a non-basic variable. But so x2 is a basic variable, and so the main thing that we need to be aware of is that our dual values will change as well, okay? And so let's call this y bar, okay? And that's going to be equal to CB transpose B inverse. But since C2 is the coefficient of one of our basis variables, this is going to change. B inverse, that's not going to change, but this will change. And so let's go ahead and write this out. So our basis variables currently are ordered x2 and then x1. And so we're going to want to actually put C2 in first and then C1. And C1's current value is this 6 right here. And so we'll want to put that 6 there. And then we'll multiply by that B inverse matrix. It's that same matrix that we used in the previous part, -1, 1, 1, -0.5. Okay, and we do the multiplication here. We multiply this row down this column, and we'll get negative C2 plus 6. And then take it down the second column, and we'll get C2 minus 3. Okay, and so that is our dual variable values and their dependence on that second coefficient of the objective. Okay, currently the current C2 is equal to 4, and if we plug 4 into there, we get the current dual variables are -4 plus 6 is 2, and 4 minus 3 is 1, and we get 2, 1. And remember, those are exactly the values that are corresponding to the objective row for the slack variables. Okay, and so that 2, 1, we could have read up straight off our optimal tableau, but it is good to make sure that the formulas that we're getting here and the dependence on C2 matches up with what we should expect with the current value of C2. So that will give us our alternate y. Maybe I'll call that y bar. Now we need to check if we change a coefficient of the objective, the main thing that we need to check is that all the entries in this objective row stay greater than or equal to 0 for a maximization problem. If this were a minimization problem, we'd want them all to be less than or equal to 0. Okay. For our basic variables, once we get it solved out to the basis, these will always be zeros here. Okay, and so once the row operations are done, those will always be zeros there. So what we do need to check are the coefficients corresponding to x3, s1, and s2, which are our non-basic variables. Okay, now we'll start with the easy ones, s1 and s2, because their coefficients are always going to be the entries of our dual variables. Okay, so let's look at the coefficient of s1. Its coefficient in the objective row is always going to be y1. And in this case, y1 bar is equal to negative C2 plus 6. And we need that coefficient in the objective row has to be greater than or equal to 0 in order for us to be in an optimal solution. Okay, and so this gives us the constraint. Let's add C2 over the other side. 6 is greater than or equal to C2 bar. Okay. For S2, we'll be looking at the second dual variable. Okay. And reading off from here, that will give us C2 minus 3 has to be greater than or equal to 0. And add the 3 over the other side, and we get C2 is greater than or equal to 3. Okay, so we've got an upper bound and a lower bound for C2. We also need to check X3. Okay, now when we look at the coefficient of X3, it's currently 1. What is that value, or what's the formula that would give us that value? Well, the formula that will give us that value is Y transpose times the column of that variable, which in this case we'll call that A3, minus the coefficient of that variable, so C3. Okay, and that needs to be greater than or equal to 0. So let's go ahead and set this up here. And so this will have these entries up here. And so negative C2 plus 6, C2 minus 3. We're going to need to multiply by the third column of the A matrix. And so let's look back here and look at our original problem. And we want to look at the coefficients of X3 there. In this case, there's no coefficients written in because those coefficients are exactly 1. So 1 and 1 are the coefficients of X1 in the first constraint and in the second constraint. And so our A3 vector here is 1 and 1. The column of X3 in the constraint matrix. And then we need to subtract off the current value of C3. The coefficient of X3 in the objective is 2. And so we'll get minus 2. And that needs to be greater than or equal to 0. Let's go ahead and do this vector-vector multiplication, where we multiply a row vector by a column vector. Whenever we multiply a row by a column, we'll get down to just a single number. So we take this times 1 plus this times 1, and that will give us negative C2 bar plus 6 plus C2 minus 3 minus 2. And that's going to be equal, well, these are nicely going to cancel out. We're going to get 6 minus 3 minus 2. That's going to be 1, and it just so happens that 1 is greater than or equal to 0. Okay. The interesting thing to note here is this 1 here, it doesn't depend on our C2 because our C2s cancel out. Okay, that's not typically the case. This one kind of specially worked out that way, but that won't always happen. And so it turns out no matter what we change the second coefficient of our objective to, no matter what we change C2 to, this coefficient here is going to stay 1. Okay, and actually looking at this optimal tableau, I kind of tip off to that is the fact that there's a 0 right here. I probably wouldn't have looked for the fact that that 0 is there, but now that I noticed that pattern, I think that 0 is why. no matter what we change the coefficient of x to, we'd then add a multiple of this up to here, and it wouldn't affect this x3 because there's a 0 right there. Okay. And so let's go ahead and box in our final answer. The lower bound for C2 is 3, the upper bound is 6. And so we get C is less than or equal to C2 is less than or equal to 6. And so any value for that second coefficient of the objective that's between 3 and 6 will leave us with the current basis. Okay, if we end up getting more profit from the second decision variable, then we might put more emphasis on that decision variable. If we get less profit, then we might switch to a basis where we're no longer using x2, and x2 becomes a non-basic variable and is set to 0. Okay. So that's question 3. This is an example of a change to the objective coefficient of a basic variable. Let's move on to question D. Let's consider a new decision variable. So let's say we introduce maybe a new product that we're now considering, and we know that it takes 2 units for this constraint and 1 unit for this constraint. But at the moment, maybe we don't know its contribution to the objective. What values of C4 will keep the optimal basis the same? Okay, and so looking at this, whenever you're introducing a new decision variable, you can consider that pretty much the same as a change to a non-basic variable, because as we introduce this variable, our assumption is that at the beginning it's non-basic, right? Because before we considered this variable, well, x4 was 0 because it wasn't even part of the problem. Now we're adding x4 in, and we're asking the question sort of, when might we make x4 not 0? Okay, so this will be just the same as if we were to change the coefficient of a non-basic variable. So give it a try, and we'll come back with the solution in just a moment. So let's look at this. And the solution, the main way that we can figure this out is by looking at the dual constraint corresponding to this new variable. Okay, for that dual constraint, we need to look at the coefficients of x4, which are 2 and 1. And then C4 will end up being the right-hand side of the dual constraint. Okay, so our dual variables, we're going to call them y1 and y2. And so these coefficients here are going to be a coefficient of y1, and this is going to be the coefficient of y2 in that dual constraint. So that dual constraint ends up being 2y1 plus y2 is greater than or equal to, we take that objective value and put it as the right-hand side. Okay. Our current basis, so for our current basis, we know the values of y1 and y2. So for the current basis, y is equal to 2, 1, and we kind of noted that earlier. So let's go ahead and plug in the values in 2 and 1 for y2 and y1. And so we'll get 2 times 2 plus 1 is greater than or equal to C4. That tells us that 5 is greater than or equal to C4. Okay, so if we get less than 5 units of profit for this new product or this new decision variable, whatever it is, then we'll keep it as a non-basic variable. So it will set x4 equals 0. On the other hand, if we get to a point where C4 is bigger than 5, then it starts being profitable to bring whatever decision variable x4 is into the basis. Okay, so that is an example of a new decision variable being added. How do you do? Hopefully this was a helpful practice problem for you.